Hello, everybody. My name is Engin Kayraklioglu. I'm a member of the Chapel team at Hewlett Packard Enterprise, and right now I'm here to talk about user experiences, which is kind of a new experience for me because we give talks about Chapel, but they are typically more technical than this one. This is going to be a more social talk, which is really an exciting opportunity for us to take stock of where we are in our community as well. If you're interested in more technical content for Chapel, this afternoon is our Chapel project meeting, so definitely stop by to see a couple of talks and hands-on demos about Chapel too. So I say in Chapel a lot. I'm assuming that you know, at least you heard of it before, but if you haven't, Chapel is a parallel programming language that is designed to be parallel and scalable from day zero, basically. It can run on multi-core CPUs, it can run on GPUs, it can run on supercomputers, anything that you have in terms of like conventional parallel hardware. It is portable. It runs on different operating systems, different networking layers, and different architectures. It is general purpose. It is something that we kind of take pride in a little bit. Our users span very different areas of science and engineering, and I will cover some of those today. It's a modern programming language, which is kind of a vague term, like what does modern mean? But in this context, it means we have things like error handling, memory and type safety, inheritance, and things like that. Stuff that are kind of orthogonal to parallel programming, but still kind of common in relatively newer programming languages out there, as opposed to things like C and Fortran. And open source, obviously, we are a member of HPSF as of several months ago. We are an established project under HPSF, and many of our meetings and discussions and things like that are all publicly available. So I will talk about community a little bit, but on Monday, my colleague Daniel Fedorin also gave a talk about supporting a community and challenges for adoption. So that was also an interesting talk from a perspective of how to grow a community, how to foster a community for an open source project like Chapel. But my talk is related, but it's more about our existing user base. So it will be more about their success stories, their pains, and whatnot. And I've been working on Chapel for a long time. Obviously, I'm biased, but I'm trying to, I will try to kind of touch upon pain points that we see in their usage of Chapel and kind of share my thoughts as I go along. So with that out of the way, there is really no typical Chapel user. And we kind of take pride in it. I really enjoy that fact. But that was kind of a challenge for this talk. Like in preparing this talk, it's kind of going to look like a grab bag of different user stories because there's no like coherent story. There's no one typical user. They span different fields, as I mentioned: earth sciences, engineering disciplines, data analytics, computer science. They use very different kinds of architectures. Some of the user groups that we have, they just stick with workstations in their lab. They never do anything multi-node, but they still use CPUs and GPUs in that workstation. Some of them use leadership class systems that are available in the labs and things like that. Some of them are strictly CPU users. They never touch GPUs. Some of them are just the opposite. They like Chapel for different reasons too. One of our user group that I will talk about is actually picked up Chapel because they simply like the language. We have first-class arrays and multi-dimensional arrays and all these kind of fancy array operations that are really high level. They picked it up because of that, but then they liked it afterwards because of parallelism and performance. And among all of these, they have different gripes and wishes too, which is kind of a balancing act for us as the developers of the language. But it's something that we kind of enjoy, that richness of the community. And most of the things that I will talk about today are based on a blog series that we run on Chapel blog. That is 7 questions for Chapel users. So we basically ask the same 7 questions to a bunch of different Chapel users. This is like a written interview, and they're all published on our blog. Right now, I think we have 8 of those. Do I count it right? Yes. And as far as I know, there are 2 other that are in the pipeline. So it's a very active and ongoing series. And I will only touch upon a small part of what we covered there. So with that out of the way, the first application or the first user story is about biodiversity. And from an HPC person, this is about going from a single core CPU execution of an application to a machine like Frontier, which was #1 in top 500 when we first did the study. So let me introduce you to this problem, and I'm definitely not a scientist in this area, so if anybody knows better, please excuse my ignorance here. So this is kind of a remote sensing application based on satellite imagery. Imagine you have a satellite image of an island in an ocean, and you want to detect whether there's any coral reefs around that island. So the idea is you take images of the same island at different points in the light spectrum, typically 5 different images with different points in the spectrum. And then what you do is just you run this big, to me at least, stencil to run convolution on these images to detect biological hotspots. And these are probably indicative of existence of coral reefs, so you can arrange expeditions, protect those coral reefs, add safety zones and whatnot. So that's kind of the goal of the application. And the sizes here are, the images are typically more than 10,000 by 10,000 pixels. And the stencil that the researchers want to run is basically a circular stencil with diameter of 400 pixels. So this is kind of a relatively large operator that you run across a relatively large image. And just recall that there's actually multiple images because this is spectral analysis. So this is a work that we did as a team with Scott Bachman, who was at NCAR back then, who's an oceanographer. Who implemented this algorithm that he had in mind, and this is kind of a brand new algorithm in his field, as far as I know. And this was implemented on CPU using Chapel. So he was just learning Chapel, he was more of a MATLAB person before that. So we implemented this algorithm in Chapel, and we collected some results, and it was completely sequential. And we calculated that for the realistic data sizes that he cares about, it would take 27 days to run this application, because it's like 6 deep, 4 loops, and everything like that. But at the same time, it's pretty much embracing the parallel application, and he had some access to GPU nodes. And back then we were just developing our native GPU support, which is in a more mature state these days, but this was kind of a good opportunity for us to stress test what we have that day and what is missing. So we ported his CPU-only, completely sequential Chapel implementation of this algorithm to our native GPU support. His code was 250 lines, and it just expanded to 300 lines. But maybe more importantly, we didn't use any new language construct that he hadn't before. So it was, Chapel GPU support is pretty much like seamless compared to other parallelisms, other ways of doing parallelism in Chapel. So we kind of gave him a code that he can actually understand. It was just slightly different. And this is still 300 lines of code, which is pretty small application. So the straightforward code changes led us from sequential code to multiple GPUs, multiple nodes, and multiple threads. And as a result, we ran this on 2 nodes of Frontier, and with the realistic problem sizes, we got the results in 87 minutes. And if you put it on 64 nodes, we ran it in 17 minutes. So as HPC people, this is not great scaling, right? Like going from 2 nodes to 64 nodes, and you're just only getting 5x speed up. So that's definitely not ideal, and as you can see from the plot. But at the same time, this was a problem that he couldn't solve with sequential programming, with MATLAB, or with sequential Chapel even. But with Chapel's GPU support, with minimal changes, we were able to take this runtime that he had, that was like February, essentially, and then we were able to run it in 90 minutes, less than 90 minutes in 2 nodes, which is relatively easy to find. And if you have more nodes available to you, less than 20 minutes. It's like a quick lunch break, right? So that was like a big achievement and big step towards his science. Not necessarily the best optimal performance from HPC sense, but it did the job. So as I mentioned, most of the stories here are based on this blog. I recommend checking out Scott's interview. The gripes that he mentioned was actually were a little bit challenging. The first one was about using a single data parallel loop to map multiple GPUs and multiple nodes. So Chapel has distributed arrays, but we haven't extended them to GPUs yet, so this was kind of a limitation. In Chapel, you can just do some lower level implementation for better control for parallelism, so you can still benefit from multiple GPUs, but you would have to write a little bit of low level Chapel still today. Installing on clusters was a big pain point for him. Since those days, we made a lot of improvements. We now ship Linux packages, and we also have a SPAC package. I don't know if you heard of SPAC before, but we have a SPAC package too. So we made some improvements. Are we there? I don't know, but things are hopefully a little bit better today. The next application I have is world-class, I'd like to call a CFD solver. And the other application was doing a lot of research in 300 lines of code, and this is on the other end of the spectrum. Last I checked, it was more than 150,000 lines of Chapel code. So it's a serious investment across multiple years and generations of developers. And this has an interesting starting story as well, because inertia is a common thing here, right? Like you don't want to refactor code, you want to keep legacy code as much as possible, and things like that. So in 2019, a group of grad students reached out to Brad Chamberlain. Brad is our technical lead, the Chapel project founding member. And they say that they want to write a CFD solver, computational fluid dynamics solver, in Chapel for aerodynamics. They are mechanical engineering students and they do aircraft design. They already have a solver in-house. This is C+ OpenMP, so it's a single node parallel implementation, but it's already getting a little bit unwieldy for them to maintain. At the same time, they are running into larger problems. They want to run multi-node, and they also want to go from 2D to 3D, structured to unstructured simulations, so there's a lot of complexity that are coming in. So they really want to rewrite what they have from scratch. And they're really interested in Chapel, these grad students. Meanwhile, their PI, Eric Lorendo, is hesitant because, you know, C++, OpenMP, MPI are kind of the de facto tools that are out there and feels much safer, whereas Chapel is practically an unknown compared to those three, right? Which is a completely understandable worry. So these grad students, Simon, Matthew, and Fred, they just implemented in Chapel nonetheless. They just go against their PI's wishes on their own free time, and they just demonstrate that they can actually do it surprisingly quickly from scratch in Chapel, achieve the fidelity against the experimental results, and can run on multi-node. So they demonstrate this to Eric, and that finally convinces him to allow the team to rewrite their application in Chapel. And then we are learning years later that actually Eric pulled a similar trick when he was young and working at a company where they have a bunch of sequential Fortran code, and he actually ported it into C as a surprise to his manager and going against his wishes. So it's kind of the breaking the inertia is kind of takes a little bit of bravery, I guess, is kind of the message here. So the end result is CHAMPS. CHAMPS stands for Chapel Multiphysics Simulation. It's developed at Polytechnique Montreal. It's designed for aerodynamics design, as I mentioned, and it's a multiphysics simulation. So flow is the core of it, but at the same time it can simulate like water droplets around the wings and how it creates ice around the wings and changes its shape and things like that, and turbulence and everything that I have no idea about. But they generate pretty cool pictures, so I really like showing their pictures as well. As I mentioned, this is a relatively big Chapel code base. To our knowledge, it's the biggest one out there. 150,000 lines was the latest count. And this is developed by mechanical engineering grad students, postdocs, undergrads who are doing summer internships and things like that. By my count, there were 22 contributors to the code so far. So it's a relatively big application, relatively big community, and an evolving community because it's an academic institution. People start their grad school, they graduate, they are done with it, then the next generation starts, and so on and so forth. So it's a very dynamic kind of environment within Polytechnique Montreal. And this achieves similar fidelity to commercially developed software, actually. So what I will show you next is Eric's interview, again, in this series, and he refers to some of these institutions, like NASA is one of them, ONERA, DLR, Japan's, basically, space institution. So they have these workshops where they compare their simulation software in terms of their fidelity and performance and things like that, and CHAMPS can compare to all of those technologies in terms of how it tracks the experimental results and the real-world results of these aircraft design. So Eric's gripes were lack of profilers, which is a big gripe. I completely agree with that. I'm definitely like a right-ln timer kind of programmer and debugger, but I understand. Faster compilation is a big pain point because we compile a lot when we do, but we also have an ongoing effort to make things better. Better error messages was something that he called out, but I think we are doing much better. You can always have better error messages, though. I think that will be a perpetual worry, right? And package manager is something that we are actively working on today, which is called Mason. So sequel to Eric's interview is coming up soon. We interviewed 3 of his current grad students who are maintainers of CHAMPS. It will be on our blog, hopefully in a couple of weeks. If you are interested in CFD, there might be some CFD folks in the crowd. We also gave a talk, Eric, myself, and a grad student of his at NASA Ames last year. So the talk is available on NASA website as well, but it's more on the technically heavy side. All right. That was Eric and his team's story with CHAMPS. The next one is a story from Brazil, and it's about greenhouse gas analysis in the Amazon rainforest. And from a technical perspective, this is a group that went from classic sequential Fortran for scientific computing to using GPUs and multi-core CPUs thanks to Chapel. So I really like this picture. I don't know how visible it is, but this is a picture of the Amazon rainforest. And if you cannot see it, especially from the back, there's actually a huge tower there, the size of the bracket that you're seeing there. So it's a really tall tower in the middle of the rainforest full of sensors. They are just collecting a bunch of data from the atmosphere on top of the canopy of Amazon rainforest, and they're analyzing its data to understand the impact of climate change and whatnot. And this is called Amazon Tall Tower Observatory. Obviously, it's a collaborative effort, but this group is one of the teams who are just looking at the data collected from Amazon Tall Tower Observatory. And this is a story about Chapel syntax. So this is a civil engineering group. As I mentioned, they were using Fortran, some Python, some C, some Pascal. They were running into issues where they weren't able to get enough performance out of these. Everything was sequential in their world. So they were looking for a language that is more performant, and Chapel was there for them, but they weren't like focused on parallelism per se. They just wanted performance, and that's it. And they really like Chapel's syntax because we have multidimensional arrays natively. You can manipulate them relatively easily. And a key point here is that this group had never done any parallel programming before. So after picking up Chapel, they realized that they can actually write parallel code really easily. It comes batteries included basically, so you don't have to add anything on top of Chapel to get parallelism. You just change your loops to parallel loops and you have better performance. So they realized this, and the performance impact that they were getting out of Chapel was much more than they expected, because they were actually going from sequential to parallel, not just using a faster technology. So now, these days, they now write everything in Chapel. Simple scripts that don't really care about performance that much, to numerical analysis code that actually cares about performance, because they just want to use a single technology, and Chapel is able to do all of these for them. And a really cool part of this story is their experience with parallelism come to a point where they purchased a GPU workstation, a relatively beefy one, for their lab to share between students and the researchers. So they were a group who had never done parallel programming before, got introduced to parallel programming because they liked Chapel, and now they are using GPUs in their lab. So technologies like Chapel can help people get into HPC or HPC adjacent technologies. I call this GPU workstation an HPC adjacent technology. And Nelson also participated in the interview here. If you want to hear him talk, his CHU 2022 talk was the most general one and discusses why he picked Chapel over other alternatives. He had other more technical talks as well over the years, but that's still my favorite. And his gripes are also interesting because he wanted smaller executables. Like, executable size is not something that we worried too much about at HPC, at least we didn't so far in Chapel. But it was interesting because they are using smaller scale systems. Probably they are just shipping around or passing around executables directly because everyone is using the same system. So that was a pain point for him, and probably still is because we haven't done much there. He also had a very technical gripe. I'm not going to dig too much into it, but it's about function pointers, so to speak, in Chapel and their flexibility. How am I doing on time? 20 minutes, okay. So this is the last story that I have, and this is about doing data analytics at scale with an application called Arcuda. But this is how Chapel can be used to power Python, because everyone wants to write code in Python, right? It's the most common language out there, but Chapel can still be used under the hood. And this is the story about that. So imagine you have a lot of data scientists that are basically trained in Python and Python libraries that are common for data analytics, NumPy, Pandas, what have you. And then you have run into a data analysis problem that is just large, and you cannot just do it on workstations and laptops, and you need to use HPC. And you do have access to HPC systems. So how can you leverage the workforce that you have that knows Python and the hardware that you have that is HPC without having to retrain them? So that's where Arcuda comes in. Arcuda is a client-server architecture, if you will, but it's a Python library that is the client. The Python library is heavily inspired by NumPy and Pandas, so it aspires to be drop-in replacement for those. So you write those code in Arcuda, but what happens is it will communicate with a server on the backend, and that server will be running on HPC systems. So if you know Python, everything will be just executed in C, like NumPy and Pandas eventually become C, essentially. In Arcuda, they will become Chapel. And that Chapel server will be running on HPC system. So you can think of it as NumPy and Pandas, but more scalable, but at the same time, its architecture is general enough, the server-client architecture is general enough that actually you can use it for anything if you extend it for other purposes as well that HPC can help with. So we've been doing a lot of performance analysis with Arcuda. The first plot that you see on the left is comparing Arcuda against Dask and Spark, which are comparable technologies for some server telemetry analysis workflow, and we are seeing that Arcuda outperforms them because we start with HPC performance in mind first, as opposed to things like reliability and flexibility. And the second plot that you see is more at scale. This is 8,000 something nodes of a Cray EX system. So this is, you can call it a leadership class system or a milling course. And this is Arcuda sorting 256 TB bytes of data in 30 seconds. So this kind of data juggling is what Arcuda is good for, and it's powered by Chapel. And as you can see, it can scale all the way up to the largest machines that you have out there available. Arcuda has a website. It has all resources, documentation. It's an open source project as well. It's not part of HPSF. It's something that we discuss a little bit. It's still in the earlier stages, but you can also check out his code. One of his co-inventors is Bill Roos, who participated in these series that I've been referring to, so I definitely recommend checking out his interview in these series as well to understand why they choose Chapel, why they built Arcuda to begin with. So in closing, I just want to highlight what I said before as this is a very social talk for me, not technical at all. And I think this is a really good opportunity that HPSF gives us. So I think it will be really important for each project to think about what their users think about their tools and kind of have these kind of, if you want, gripe sessions where developers get together and talk about users' issues, because I believe there's a lot of common issues, call it benchmarking, for example, or installation on new systems and things like that. So I think it's really important for us to have these kind of conversations that are more social than technical to have a better community for HPC, I think. With that, thank you so much. I'll take any questions if you have it.
Thank you for your talk. I really liked how you curated the user stories. Can you share a bit your process, how you go about collecting these user stories, and if you have anything to share with other projects, thing to avoid, and what works, what doesn't?
Sure. So I think we started this series maybe a year and a half ago, and procedurally what we have is, I'll just go down to the nuts and bolts. We literally have a Word document that has 7 questions in them. And under each question we have some hints, like think of this, think of that, to basically get the blood running in people's minds, right? Because if you just see a single sentence question, like how do I answer this? So we have those kind of little hints under each question, not necessarily leading or anything, but just to give them an idea. And we basically reach out to our users who are invested in the project, not just passers-by, because we are open source project. That happened a lot too, right? Like someone just creates an issue and then falls off the face of the earth. So it's not like everyone who show their nickname, but it's more about people that we interact with. So I think that's what we have been doing, and we are trying to sort of like run a pipeline so that we reach out to a couple of users, wait for their responses to come back, edit it a little bit, and then we reach out to other users so that we have things going on. So I think it has been working out relatively smoothly. We are doing more and more like multiple people contributing to the same interview. There has been some challenges with that because some of them are not following through and some interviews just are half done and we just kind of had to ignore them for a bit. So those frustrations happen, but in general it has been a very positive experience and our users have been very welcoming and helpful. So I definitely encourage doing similar things. One of the interviews that we did, actually, we did over Zoom. We transcribed it and we just wrote it down because the user didn't want to just write things down, but they were okay with, okay, let's just schedule a call and I will just answer questions live. So that's another option in terms of logistics that can help users' life easier. That was a good question. Any other questions, comments? Meanwhile, I don't know who's next, so if you're presenting next, maybe you can get set up.
Thank you.